Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 25, Organic Chemistry 2. Today we will continue on chapter 5, enols, enolates, and the alkyl condensation. In the previous lecture we covered acidity of aldehydes and ketones, keto-enol equilibria, and alkylation of aldehydes and ketones. Today we will continue on the alkylation, and we will cover the halogenation of aldehydes and ketones. Alkylation of enolate. A milder alternative to direct alkylation of enolate ions is the formation and alkylation of enamine derivatives. The carbonyl compound with alpha hydrogen reacts with secondary amine like pyrrolidine in presence of catalytic amount of acid, leading to the formation of enamine. Reaction of this enamine with alkyl halide will lead to the formation of iminium salt, which upon hydrolysis furnish the alkylated carbonyl target molecule. Formulate the mechanism for the final step of the sequence just shown: hydrolysis of iminium salt. Iminium salt in resonance structures, either the nitrogen has a positive charge or this carbon carries the positive charge. This is the structure of the iminium salt. Will react with water to form this species, carbon O bond, deprotonation with molecule of water, form this compound. Again, that will protonate one more time, but this time on nitrogen. Here is oxygen, O bond. Now it's became nitrogen H bond, followed by ejecting this species by the lone pair of oxygen to form a double bond. Deprotonation using another molecule of water will lead to the target molecule. How does the alkylation of any enamine compare with the alkylation of enolate? Enamine alkylation is far superior because it minimizes a double or multiple alkylation. Under the condition of the process, the iminium salt formed after the first alkylation is relatively stable and unable to react with additional haloalkane. If you have example like this one, carbonyl compound like this one, we have here two alpha hydrogens. In the presence of LDA, THF, followed by alkylation with this species, we get the dialkylation in 90% yield. We were not able to stop the reaction at the monoalkylation step. If this is our target molecule, this condition will not be favored. So enamine can also be used to prepare alkylated aldehyde. And we know that aldehyde enolate is very sensitive to aldol condensation, and we get next lecture. So isobutyraldehyde with pyrroline, followed by ethyl bromide, followed by hydrolysis with acidified water, will give 2,2-dimethyl butanal in good yield. The enamine derived from the unsymmetrically substituted ketone such as 2-methyl cyclohexanone, reacts with an alkyl halide to give substitution on the less substituted carbon. If you have this molecule with already substitutes on that carbon, via base catalyze we will get the alkylation on the same carbon. Okay? Now if we use the enamine will form this isomer over this one, because in this one we will have here sterically effect, so it will be not energetically favored, and the product will be that one. If this is the enamine formed, then the alkylate product will be on this side, the less substituted. Okay, R prime X, and the iminium here salt can be hydrolyzed to the carbonyl. That's our final product. If you would like to read more, that will be Stork et al. In Journal American Chemical Society in 1963, page 207. Give the expected products of the following acid catalyzed reactions: acetophenone with methylamine. Methylamine is primary amine, so what you get is actually the imine double bond in here. Instead of double bond O, you will be double bond N, and whatever the substituent on this nitrogen. Okay? On the other hand, acetophenone with dimethylamine, that's secondary amine, you get single bond in here, and the double bond will be on with the alpha. Okay, so here you get enamine, and when you react it with primary amine, you get imine. That will be NN dimethyl prop 1-ene 2-amine. Show how you would accomplish each conversion using an enamine synthesis with pyrrolidine as a secondary amine. How you can transfer cyclopentanone, this compound, to 2-allyl cyclopentanone, that one. Okay, starting with the target molecule here, this connection approach, this is the alpha position to carbonyl, so we will cleave on that. This will be negative, and this species will be positive. This is the senson, and for the enolate, we mentioned that enamine is enolate equivalent. So this is the synthetic equivalent, and for the allyl carbocation, the allyl bromide will be the synthetic equivalent. So reacting this species with that, okay, will lead to the formation to the target. How we can get this enamine? Again, we cleave in here. This will be the double bond, and here an H. Starting with pyrrolidine and the cyclopentanone in catalytic presence of catalytic amount of acid will give the enamine. Alkylation with allyl bromide will give the iminium salt. Hydrolysis the iminium salt will lead to the formation of the carbonyl target molecule. Straightforward reactions. From pentanone, pentane 3-on, to 2-methyl 1-phenyl pentane 3-on. From this one to that one. So this is the skeleton here. It is the same in here. This is alpha. So this will be the substituted. This is the substituent, or what we are going to get in here. Got in here. This will have the negative, and this carbon will have the positive. This will be the synthetic equivalent enamine, which we can get from our starting material with pyrrolidine, and the benzyl cation will be benzyl bromide, reacting the carbonyl with the secondary amine will get the enamine. Reacting the enamine with benzyl bromide will get the iminium salt. Hydrolysis the iminium salt will get you the target molecule. Alpha halogenation of ketones. Base promoted halogenation. Carbonyl compound with alpha hydrogen reacts with halogens in presence of base to form the alpha halogenated derivative. Well, the mechanism: first step, deprotonation, enolization, form enolate ion. Enolate ion will attack on halogen, the partially positive center, kicking X minus out and forming alpha halogenated carbonyl compound. This species can undergo further halogenation, again deprotonation, enolization, followed by nucleophilic attack on the halogen to form disubstituted. If we have one more, with the same process will go on. Okay, now looking for the enolate here. The enolate here is stable via the electron withdrawing effect of the halogen, the negative inductive effect. All right, that's why di and tri halogenation will take place. Haloform reaction. If we have carbonyl compound with alpha methyl group attached to it, in presence of chlorine, bromine, or iodine, in presence of base, this reaction will go on until you form the trihalo alpha, trihalo compound. Then the OH minus will attack on the carbonyl, okay, to form this anion. The oxygen lone pair will go back, form double bond, kicking the CX minus species out, stabilized again by electron withdrawing group of the halogen, which will abstract hydrogen from the COOH to form the carboxylate and haloform. In presence of iodine, this will be a precipitate, okay, yellow precipitate. When the halogen is iodine, haloform product will call iodoform, is a solid that separates out as a yellow precipitate. This iodoform identifies methyl ketones. They call it iodoform test. If we have alcohol, like the one we have in here, carbon OH to it CH3. Iodine is an oxidizing agent, so the first step will be the formation of the ketone, and in presence of base, this will be tri-substituted to form iodoform as a yellow precipitate. Predict the products of the following reaction: cyclopentyl methyl ketone, excess chlorine and sodium hydroxide. Well, we have here carbonyl, we have here CH3. So what we are expecting, trihalogenate in here, and cutting this, forming the carboxylate, so it will be sodium cyclopentacarboxylate, and HCCl3 chloroform. Recall, base catalyzed isomerization of an substituted ketone, racemization of optically active 3-methylpentane 2-on. If we have carbonyl compound with alpha chiral center in presence of base and alcohol protic solvent, we lose the chirality of this optical activity of this species. Why? Because in the presence of base, you form the enolate achiral species, which gets protonated either way to form S back or R configuration on that center. So you have RS mixture in 50-50 and you get racemic mixture. So keep in mind when you plan synthesis of chiral species. Acid promoted halogenation, carbonyl with alpha hydrogen reacts with halogen presence of catalytic amount of acid to form the alpha halogenated analog. The first step is protonation, followed by deprotonation to form the enol. Attacks of the enol to the halogen alpha partial positive, partially positive center, kicking X minus out, leads to the formation of carbocation, which in resonance with this species oxygen has a positive charge, resonance structure. Deprotonation will lead to the formation of the alpha halogenated carbonyl, last step. Why is further halogenation retarded in acidic medium? The answer lies in the requirement for enolization. To repeat halogenation, the halocarbene compound must enolize again by the usual acid catalyzed mechanism. However, the electron withdrawing power of the halogen makes the protonation, the initial step in enolization, more difficult than the original carbonyl compound. So having the alpha halogenated in first step, protonation will form this cation, which is unstable via the electron withdrawing effect of the halogen. Remember that we have anion intermediate in the base catalyzed halogenation, and the electron withdrawing effects of the halogen X will enhance the stability. But in this case, because we have a positively charged intermediate, this means that it will be unstable by the electron withdrawing effect of the halogen. Unlike ketones, aldehydes are really oxidized, and halogen are strong oxidizing agent. Attempt to halogenate aldehyde usually result in oxidation to form carboxylic acid. So aldehyde with halogen in presence of water, this is an oxidizing agent. Aldehyde will be oxidized to carboxylic acid. Acid catalyzed halogenation is synthetically useful for converting ketones to alpha beta unsaturated ketones, which are useful in Michael reactions. Propose a method for converting cyclohexanone to cyclohex 2-ene 1-on. Starting with cyclohexanone, chlorinate in acidic medium, so using chlorine acetic acid, you get 2-chlorocyclohexanone. You have here hydrogen, so reacting these compounds with potassium hydroxide and heat will go through E2 mechanism, so the base will attack the hydrogen, forming double bond in here and Cl out to form cyclohex to ene 1 on target molecule. See you next lecture.